In this video, we discussed the fundamental theorem of calculus. We're actually not going to do the proof in this video, but I'm going to tell you what the fundamental theorem of calculus says and how to apply it to evaluate definite integrals. So this tells us actually the relationship between an antiderivative of our function f and that definite integral, which represents that net area concept we talked about in the last couple of videos. The fundamental theorem says, or one part of the fundamental theorem says, that if f is continuous on the closed interval from a to b, and f is any antiderivative of f, so of course that just means that f prime of, or capital F prime, excuse me, is equal to a lowercase f of x, then the integral from a to b of f of x is the antiderivative evaluated at b and a, and then you subtract them. Now, the statement of the fundamental theorem in this particular textbook says that f has to be continuous, but it turns out that this equation still holds if f has a finite number of jump discontinuities on the interval from a to b. So let's say we're asked to evaluate this integral. We could graph the area, see what it looks like, see if that function happens to be 0 on the interval from 0 to 4, and then we would be talking about finding the area bounded by this function and the x-axis. If the function is positive sometimes and negative sometimes, it's the area bounded by the function in the x-axis that is above the x-axis minus the area bounded by the function in the x-axis that's below the x-axis. But we're just going to get a number when we're done. Now, in order to evaluate this, I have to rewrite this expression, which is called the integrand, so that my basic rules apply. And right now it's a product, so my basic rules don't apply. So we will have to rewrite it as the integral from 0 to 4 of this function times this function. Now, we don't have any rules involving square roots, but we remember that the nth root of x to the m is x to the m divided by n. And with a square root, there's an implied 2 there. And if you have an x, that's just an x to the first. So this square root of x is actually an x to the 1/2. I still don't have a rule for that. But if I distribute that x here, or that x to the 1/2 there and there, I have the integral from 0 to 4 of 2 times x to the 1/2 minus x to the 1/2 times x to the 3/2. You just add the exponents. That's going to give us an x to the 4/2, or x squared. And then we say, do I have a rule for that? We do. We have the power rule for this one, the power rule for that one, and we just subtract them. So when we want to compute the antiderivative using this part of the fundamental theorem, it's actually relatively simple. You rewrite the integrand as necessary until you have a basic rule so that you can compute that antiderivative. Then you compute the antiderivative of that function. So I'm going to bring the 2 down, then we add 1 to the exponent. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. And then we divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. And then we multiply straight across there to simplify. We'll get 4/3 times this x to the 3/2 power. And then here we're going to use the power rule again. Add 1 to the exponent and divide by the new exponent. Dividing by 3 is the same as multiplying by 1/3. And so we get this expression, and we evaluate at 0 and 4. And then we subtract. So we get 4/3 times 4 to the 3/2 minus 1/3 times 4 cubed. Minus this expression evaluated at 0. 0 to the 3/2 is 0, and 0 cubed is 0. So we just get a 0 there. And then you say, okay, well, how do I evaluate that? Well, remember this 4 to the 3/2 can be written in a radical form. Since there's a 2 in the denominator, we can take the square root of 4. And then we can cube it. And 4 cubed is actually 64. So we take square root of 4, which is 2. 2 cubed is 8. So we've got 4 times 8 divided by 3 minus 64 divided by 3. So you have 32 divided by 3 minus 64 divided by 3, which is negative 32 over 3. And that's it. It's relatively simple, very straightforward. All you have to do is rewrite the integrand if necessary, so that your basic rules apply. That's just so that we can compute that antiderivative. And then after you've done that, compute the antiderivative using your rules. And we can add a plus c, but it's not necessary because we're gonna take those two function values and subtract them. So if I added c, and then I would ultimately subtract c, and the c's would just cancel. So we compute an antiderivative, then we evaluate f at the upper limit, in this case 4, and the f at the lower limit 0, and then you subtract. You can do a little bit of arithmetic, and you simplify, and that's your final answer. Now this again represents sort of a net area. If we want to see that area, we can look at this function on this interval and see what it looks like. Let's do that on Desmos. All right, so here's my function, the square root of x times the quantity 2 minus x to the 3/2. I wanted to rewrite this as x to the 1/2, and then I distribute 2 times x to the 1/2 is 2x to the 1/2, and then x to the 1/2 times x to the 3/2 is x to the 4/2, which is actually x squared. Looks like I made an arithmetic error. So if that's my function, the integral from 0 to 4 of f of x can be computed by Desmos as negative 10.67 or 0.6 repeating. And I think that's exactly equal to the answer that we got on paper. It was negative 32 divided by 3. And say, okay, well, how do I compute that using the fundamental theorem? First, we do what we just did, bring the 2 down, add 1 to the exponent, divide by the new exponent. Dividing by 3/2 is multiplying by 2/3. And then here we add 1 to the exponent and divide by the new exponent. And so we evaluate, or we simplify this expression on paper. So we call that 4/3 times x to the 3/2 minus 1/3 x cubed. Evaluate at 4 and 0 and subtract. And we get this answer, which is the same as that answer. So we know we did it correctly. You might say, well, what does that actually look like? Looks like this. We're taking this area here and we're subtracting that area. This function is equal to 0 at x equals approximately 1.5874. So I had Desmos graph the area between 0 and the function on the interval from 0 to that x value. And then I had Desmos shade the area from the function to 0 from this x value to this x value. And so that's how I got my picture there. Now, if we want to, we could calculate this area and we could calculate that area and then subtract them by evaluating the area or the integral from 0 to that 1.5874. We get that. And then the area from 1.5874 to that negative, or to that 4. And it turns out that that area is 12 square units. That area is about, it looks like 4/3. And then if we take the 4/3 and we add the negative 12, I think we get that negative 10.6 repeating, or negative 32 divided by 3. So that's 4/3 minus 36/3, which is negative 32/3. So yep, that's right. That's how we do that. So that's our first example. Now let's look at our next example. Let's say we have the integral from 1 to 3 of 4x cubed, excuse me, minus 3x squared plus 1. So we've got a polynomial, and again, we're looking at that net area concept between x equals 1 and 3. Very easy to compute this. We look at the integrand and we say, do we have a rule for that? And we certainly do. We can just take the antiderivative term by term. This requires the power rule, so does this, and this is the constant multiple rule. The antiderivative of 4 times a function is 4 times the antiderivative of the function. Then we add 1 to the exponent and divide by the new exponent. Dividing by 4 gives us a coefficient of 1 there. Here I'll bring the negative 3 down. Then I use the power rule again, add 1 to the exponent and divide by the new exponent. The 3 is reduced there. And then the antiderivative of 1 with respect to x, it's just that 1 times x. It's always the antiderivative of a constant with respect to your variable. It's just a constant times a variable. So that's our antiderivative. We evaluate it at 1, we evaluate it at 3, and we subtract. So we're going to have 3 to the 4th minus 3 cubed plus 3 minus this expression evaluated at 1. So 1 to the 4th minus 1 cubed plus 1. Super simple. Compute the antiderivative, evaluate f at 3, evaluate f at 1, and subtract. This is 81 minus 27 plus 3. And then I've got 1 minus 1 plus 1 is 1. I have 80 minus 24, which is what, 56? And so the area between this function and the x-axis and the vertical lines x equals 1 and x equals 3 should be 56 if we've done everything correctly. So let's look at that graph on Desmos.com. So here's our graph. It's a cubic polynomial, but we're just interested in this part between x equals 1 and x equals 3. Actually got a very large y value at x equals 3 of 82. So that's our area. And the function's positive there. So we really are just getting an area between this function and the x-axis and the vertical lines x equals 1 and 3. In order to do that, we compute the antiderivative as we did on paper. We get the same answer on paper that I had already typed online. Evaluate that at 3, we get 57. Evaluate at 1, we get 1. F of 3 minus f of 1 is 56. So that means this area is 56 units squared. Or in general, that the value of the integral is just a number, and that number is 56. So this is example 3. Got some trig functions this time. We want the integral from 0 to 3 pi of this function. We say, do I have a basic rule for that? We do. First, we compute the antiderivative. We bring the 2 down. We say, what do I take the derivative of to get cosine of x? Sine of x will work. And I say, what do I take the derivative of to get negative sine of x, cosine of x? So that's my antiderivative. I plug in 0, I plug in 3 pi, and I subtract. And so I get 2 sine of 3 pi plus cosine of 3 pi minus 2 sine of 0 plus cosine of 0. And cosine of 3 pi is negative 1. Cosine of 0 is 1. Sine and cosine, sine of 3 pi and sine of 0 are both 0. So I end up with negative 1 minus 1, which is negative 2. So very, very easy. We just compute the antiderivative using our rules and then evaluate at 3 pi and 0. Let's look at the graph online. So here's our function. If we shade the region between the function and the x-axis on the interval from 0 to 3 pi, this is what we see. Now notice it's just a shifted sinusoidal function. It just looks like sine and cosine. It's the same basic shape. It's just been shifted. It looks like negative or 0.46 units to the left of where it might typically be if it was a cosine function. And that it looks like the largest y value is approximately 2.23. So it's got a different amplitude than we might expect. It's got a little bit of a shift of 0.46 units to the left. But this is the area that we're interested in. Now, because it's just a shifted sinusoidal function, this purple area here and this blue area are the same. So when I take the integral from 0 to 3 pi, I think I should get the same value as if I took the integral from 0 to pi, because this area minus this, or this area minus this area, excuse me, is going to be 0. And then we're going to take this purple area and subtract that blue area, which is the same. This area here is the same as the area from this 0 of the function to pi. Now, we don't actually need to see that to find the value of the integral. All we do is take the antiderivative as we did on paper, evaluate it at 3 pi, evaluate it at 0, and subtract. We get negative 2. But because the function is periodic, and I see that it's repeating, I wanted to confirm that I get the same answer if I integrate from 0 to pi as we do when we integrate from 0 to 3 pi. So I evaluated the integral from 0 to pi instead, and I got -2 as well. And we can see that geometrically if we look at the graph like that. All right, easy breezy, very easy. All we have to do is compute the antiderivative, plug in the bounds, and subtract. Now this one is a little bit more interesting because it's got an absolute value on it. Remember that the absolute value of x just gives us x whenever x is greater than or equal to 0. Because the absolute value of x is just the distance of that x from 0. If the value is positive or 0, we just get the number back. Now, if that value is negative, that value we're taking the absolute value of, we multiply it by -1 so that a negative times a negative gives us that positive answer we're expecting. So when x is negative, absolute value of x is -x. That's why we see y equals x when x is greater than 0, and y equals -x when x is less than 0. Like the rest of y equals -x is right there. The rest of y equals x is right there, but we're only interested in that part on these bounds. So here's x when x is positive or 0. Here's -x when x is negative. So we get that absolute value shape. And that's exactly what we're looking at here, except it's been shifted a little bit. And because we multiplied the x values by 2, we can say it shrinks it in a horizontal direction, or we can say it stretches it in a vertical direction. Either way is fine. But we can interpret this in the same way that we interpret the absolute value of x. The absolute value of 2x minus 3 is going to be 2x minus 3 as long as 2x minus 3 is positive or 0. Because the absolute value of 0 is 0. And then when 2x minus 3 is negative, we're going to take that negative number and we're going to multiply it by -1 to get the positive answer. Now, if we take these inequalities on the right and add 3 to both sides and divide by 2, we see that this is our function when x is greater than or equal to 3/2. And this is our function when x is less than 3/2. If we distribute that negative and then write the 3 first, we have 3 minus 2x on that interval. So this function is going to have that V shape, but it's going to be a line with a positive slope to the right of 1.5, and it's going to be a line with a negative slope to the left of 1.5. And 1.5 is on our interval. So when we are evaluating the integral from 0 to 6, we're actually going to see two triangles. At 1.5, our function is 0. When x equals 0, we have the absolute value of 3, which is 3. And so the graph looks like that. And then at x equals 6, the y value is very large. I don't know what it is. But that's essentially our region. We're taking this area and we're adding this area. Now, I have some options. If I want to find the value of this integral, I can use geometric formulas again, like we did before. We can just use those area formulas for the triangles. Say 1/2 base times height for that area, 1/2 base times height for that area, and add them together. Or we can use these functions to rewrite the absolute value and then integrate from 0 to 1.5 and then 1.5 to 6 as an application of the fundamental theorem of calculus. Let's do the simple way first. We've got the integral from 0 to 6 of the absolute value of 2x minus 3 is the area of this first triangle, which is 1/2, the length of the base, which is 3/2, times the height, which is 3. And if we multiply straight across, we get 9 divided by 4, or 2.25. Now here, we're doing pretty much the same thing. We've got 1/2 times the base, which is 4.5, or 9 divided by 2, right? Is that right? Yeah, 4.5. Times the height, and I don't know what that is. It's the function value at 6. When I substitute in x equals 6 here, I've got 2 times 6 is 12. 12 minus 3 is 9. So I'm multiplying by 9 over 1. So this is 81 divided by 4. So we end up with 20.25. And when we add those together, we get 22.5. So that is one way to compute that area. You might say, well, what's the other way? Well, I could take that interval from 0 to 6, and because of our properties, we can say the integral from 0 to 6 is the same as the integral from 0 to 1.5 of the function, plus the integral from 1.5 to 6 of the function. And then we say, okay, well, what is the function on these intervals? Well, on this interval from 0 to 1.5, it's that part of the line with the negative slope. So it's at 3 minus 2x. And we can use the fundamental theorem of calculus on this integral. And then on this interval, our function is this line with the positive slope. It's at 2x minus 3. We can use the fundamental theorem on this one, taking the antiderivative and then plug in the bounds and subtract. So we'll do that. The antiderivative of a constant with respect to x is that constant times x. Bring the negative 2 down, then add 1 to the exponent and divide by the new exponent. So we just get 3x minus x squared for our antiderivative. And we substitute in 1 and we substitute in 3 halves. So we end up with 3 times 3 halves minus 3 halves squared minus this function evaluated at 0, which is just 0. And I'm using 3 halves because it's easy to do the arithmetic that way. I don't really think in terms of decimals when I'm doing arithmetic. Now, similarly, here, I'll bring the 2 down, add 1 to the exponent, divide by the new exponent, the 2's reduce. The antiderivative of negative 3 is negative 3 times x. Substitute in 3 halves and 6 and subtract. So when we substitute 6, we'll have 6 squared minus 3 times 6. Oops. And then we'll subtract a 3 halves squared minus 3 times 3 halves. And if we simplify, it's 3 over 1. We got 9 halves minus 9 fourths plus 36 minus 18 minus 9 fourths. And if we distribute that negative, we'll say plus 3 over 1 times 3 over 2. So we're going to add 9 halves. 9 halves plus 9 halves is 9. Negative 9 over 4 minus 9 over 4 is negative 18 over 4, or 9 over 2. 36 minus 18 is 18. So we end up with 27 minus 9 divided by 2. If we multiply by 2 over 2, we get 54 minus 9, all divided by 2, which is 45 over 2. And 45 over 2 is 22.5. And that is the same value as we got over there. So super simple. We're just taking the antiderivative, plugging in the bounds and subtracting, but it's a little bit more complicated because of that absolute value. Just remember, if you have the absolute value of a function, we're going to get the function when the function is positive, the opposite of the function when the function is negative, and you get just 2 branches to a piecewise function. If you have to integrate that function over a particular interval, just make sure you know what that function is without the absolute value bars, and then integrate over that interval. If you do, you'll get a positive answer each time because that integral, or because the absolute value of a function is always going to be positive. So we got over here, if we wanted to evaluate that, we'd get this 9 halves minus 9 fourths, which is going to be 9 fourths, or 2.25. So we're going to have 2.25 here. Plus this value, I think, which is like 20.25. Then when we add them together, we get that 22.5. The same as what we got when we just looked at the area of the first triangle, added the area of the second triangle. You get the same thing. I like the triangle approach actually with this particular problem because it's much simpler than using the fundamental theorem. But this is a good exercise, especially if that function inside the absolute value bars is more interesting than a linear function. Like what if it involved an x squared or an x cubed or something like that? Then we might want to apply this property of absolute value to find the function on various intervals and then integrate the function over those intervals using the fundamental theorem. If we look at the pictures online, we see pretty much the same thing. So there's our region. We get 45 over 2 if we just use Desmos. It says 22.5, so we know we did our calculations correctly when we did them by hand. And this graph goes through everything that we just talked about. The 2.25, the 20.25. And then how, when we add those two together, we get the 22.5. Okay. Last problem, excuse me. It says we find the area of the region bounded by the function below and the x-axis. So I've got f of x equals 2 times the square root of x minus x. Now this is one where I might be able to guess the x values where that function crosses the x-axis, but it's not a standard function that I know the graph of. I know what 2 times the square root of x looks like. I know what x looks like. But when I take that radical expression and I subtract that line or that linear expression, I don't necessarily know what the graph looks like. I might have some sense of what it looks like, but it's not necessarily obvious to me what the intercepts are unless I set it equal to 0, get the radical expression by itself, square both sides, like unless we do a lot of algebra. So we could do that algebra on paper to find the y-intercepts of that, or we could just graph the function online. When we graph it online, we say, well, when x is 0, we get 0. That makes sense. And if I substitute in x equals 4, I also get 0. So when it says find the area of the region bounded by the function below in the x-axis, I know that I'm just going to integrate from 0 to 4. And so looking at the graph online helps us to visualize the function. It gives us our bounds, and then we can just apply the fundamental theorem. So I rewrote that that square root of x is x to the 1/2, and then I just use the power rule to compute the antiderivative. Bring the 2 down, add 1 to the exponent to get that 3/2, divide by the new exponent. Dividing by 3/2 is multiplying by 2/3. 2 times 2/3 is 4/3. And then I use the power rule for the x to the first. Add 1 to the exponent to get x squared. Divide by the new exponent to get 1/2. Then you plug in 4, you plug in 0 and subtract, and you get 8/3, which is that 2.67 or 2.6 repeating. That's exactly what we would expect. So that's how we would do that. Now, if I did not have the graphing calculator, I could still figure that out, figure out what the graph looked like, but I would have to do some calculations on paper. So let's do that, and then we'll be done with this video. Okay, so if I'm given this and I don't know what the graph looks like, I remember this area bounded by the function and the x-axis is going to require us to find those x values where the y values on this graph are 0. So I'm going to set the y equal to 0 or replace f of x with 0 and then solve for x. Now this is an equation involving a radical. So to solve this, I'm going to get the radical expression on one side and then all the other terms on the other side. I'll do that by adding x to both sides. And then to get rid of the radical, we'll square both sides. So square that and then square that. So we get x squared here. Now you've got a product here, so you square the 2 and you square the square root. So 2 squared is 4, and the square root of x squared is x. But I want you to remember this original function was only well-defined for x greater than or equal to 0. We can't take the square root of a negative number. So this equation is not equivalent to this equation, but the solutions of this equation are included in the solutions of this equation. So if this is true, then this is true, but there might be some solutions of this that aren't actually solutions of that. So we got x squared equals 4x, and we want to require x to be greater than or equal to 0 because that was the original domain of this function. I'll subtract x from both sides, or 4x from both sides, and then we see that factors. X squared and 4x have a factor of x in common. X times x gives me x squared. X times -4 gives me the negative 4x. And if that times that equals 0, either x equals 0 or x equals 4. So those are our intercepts. That's how I would find that without a calculator. And then you might say, okay, well, those are the only places where that function could change from positive to negative or negative to positive. So I might want to know on the interval from 0 to 4, is the function positive or negative? Well, I can just substitute in x equals 1. When x equals 1, I get 2 times the square root of 1, which is 1. And so I have 2 times 1, which is 2. And 2 minus 1 is 1. So we plug in a value, and we know that the function is positive there. So now I don't know exactly what it looks like, but I know that it's going to look something like that. That's just from the graph online. But I know that since the y value at x equals 1 is positive, that the graph is going to pass through this point and then it's going to do something. It has to go from here to here somehow, and it has to pass through that point. Now, to the right of that, if I plug in, say, x equals 9, f of 9 is 2 times the square root of 9 minus 3, or excuse me, minus 9. The square root of 9 is 3. And I get 6 minus 9, which is negative 3. So we see we get a y value of negative 3 there. And that function is never crossing that x-axis again. It only crossed the x-axis at x equals 0 and 4. So it just keeps going. If we're asked for the area bounded by the function in the x-axis, and that function just continues to go to negative infinity as x goes to positive infinity, we must be talking about that area. So in order to find this area, first we figure out where that function crosses the x-axis, and then we think about whether that function is positive or negative there. And then that allows us to visualize what we're finding. We know we're finding this area above the x-axis, and because the function's positive, I'm expecting a positive answer. And now I can use the fundamental theorem of calculus to find that value. So we've got the area is the integral from 0 to 4 of 2 times the square root of x minus x. We'll rewrite that square root of x as x to the 1/2. Bring the 2 down, add 1 to the exponent, divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Add 1 to the exponent, divide by the new exponent here. Substitute 0 and 4 and subtract. End up with 4/3 times 4 to the 3/2 minus 1/2 of 4 squared. And then we evaluate that at 0 and we get 0. So we've got 4/3 times the square root of 4 cubed minus 16 divided by 2, which is 8. This is 2 cubed, which is 8. Times 4 is 32 divided by 3 minus 8, which is 24 divided by 3. 32 minus 24 is, what is that? 32 minus 24. Is that 8? 8/3? Yeah, it's 8/3. And that is what? 2 2/3, or approximately 2.67, or 2.6 repeating. And that's the same answer that we got. Okay, so that's it for the fundamental theorem. We did not prove it, but we did show how to use it to evaluate an integral. You rewrite the integrand as much as possible so your basic rules apply. Anti-differentiate using your rules. Plug in the upper bound and the lower bound and subtract. And that's it. And then when you're done, you look at the pictures, or you draw the pictures yourself, and you interpret it as area. If the function's above the x-axis on the interval, it's the area between the function and the x-axis. If the function is above the x-axis for part of the interval and below it for the other parts, it's this area above minus the area below. So if we were asked to integrate from 0 to, say, 9, we'd have this area minus this area. But this time we were asked for the area bounded by the function in the x-axis. So we figured out what those bounds were ourselves, by setting the y value equal to 0 and solving for x. And then we said, okay, well, where does that x-axis, if that's one boundary and that's one boundary, what is the area in between? And we said, well, that's got to be the area in between.